went off, of course. Alright, so today's 3.1c, which is the last section of 3.1, which is derivative of function, and we're going to talk about how we can sketch the graph of the derivative. So we've already learned in this class that how to use the formulas, right? So you can use the formula to find the derivative of a function. So if you were to use the formula to find the derivative of f of x equals x minus 3 squared, you would get 2x minus 6. So what you're always going to notice is when you take the derivative of a function, it's always going to go down a degree. Okay? So if it's to the second, it's going to go down to just the first, x. If it's to the fourth, if it's a fourth degree polynomial, it's going to go down to the third. It's going to be cubic. If it's to the third degree, it's going to go down to the second. So you're going to notice that when you go to sketch the derivative, it's always going to go down 1 degree. So we know quadratic is second degree, which its derivative becomes linear, right? If it's linear to begin with, it's going to go down to constant, which is a horizontal line. So that's kind of like a way to, as you go into it, think about the fact that your sketch should look that way if it is one of those type of classifications of functions. Alright, so we're going to look at something that doesn't have an exact equation. So I couldn't come up with an equation, a simple equation to model this graph, of course, because it's just kind of jumbled, right? So we're going to talk about how we can estimate the graph of the derivative. So the derivative we've learned is basically instantaneous slope, right? It's slope at a certain point. So what we're going to do is we're going to estimate the slope at a bunch of points on this graph, and then we're going to graph it. So when you go to graph the derivative, the y-axis acts as the slope. So whatever you get as the slope is going to be what you graph as the y-coordinate to that point. So let's go ahead and try the first one. So what would you estimate, if you were to draw a tangent line at this point, what would you estimate that slope to be of this tangent line?
What?
Not 1, but... Oh, it's going downward, right?
Negative 1.
-1. So you would say the slope here is about -1. You might say negative 0.5. But the main thing is you know that it's not.
There's no way you call that negative 0.5.
Yeah, I'd say it's 1. Yeah, that's true. So at this one here, if you were to draw a tangent line, isn't that tangent line going to be like a horizontal line like this?
Mm-hmm.
So what would be the slope of this line right here? What would be the slope of a horizontal line?
0.
0. Good. Okay. Now we're going to draw a tangent line at the point at -1. What would you estimate that slope to be? I would say it's +1, right? It's about up 1 over 1. So +1. Okay. What would you estimate the slope to be at 0? 0. Okay. What about this one here? Yeah, -2 or -1.5. I'm going to go with -2. What about here at 1? Good, -1. And I would also estimate at 1.5 to also be -1. What would you estimate the slope to be at 2.5?
0.
Good. What about here at 3?
2.
Good. And then this, I would say, is also 2. Okay. So now that we've estimated the slopes at a bunch of points, we're going to go ahead and talk about how we can graph this. So you can write it out as coordinates if it makes it make more sense to you, but you don't have to. So we estimated at 3.5 that the slope is what?
1 or -1.
-1. So we plot at -3.5. We plot at 1 or -1. What did we estimate the slope to be at -2?
0.
So we plot at 0 and -2. What did we estimate the slope to be at -1? So we plot at 1. What did we estimate the slope to be at 0?
0.
So we plot at 0. What did we estimate the slope to be at 0.5? So we plot at -2. What did we estimate the slope to be at 1? -1. So we plot at -1. What about at 1.5? -1. What about at 2? 2.5. So we plot at 0. At 3, we estimated it to be
2,
and at 4, we estimated it to be also
2.
2. So now we can connect this. So what you've just graphed is the instantaneous rate of change graph for the function. So you basically just graphed the derivative function. So that's how you do it. So you basically estimate slopes at each point, and then you can graph the slope as the y-axis of the derivative graph. Okay? All right. So now we're just going to analyze this so you can have a better understanding of what's happening here. So as you can see, we have the function x cubed minus 3x plus 3. What classification of polynomial is that? Cubic, right?
Mm-hmm.
Cubic, which means that its derivative is going to go down 1 degree, so it's going to be quadratic. Okay, we already knew that going into it because we know it always drops a degree. So looking at this, we're just going to analyze some points so you have a better understanding of how one relates to the other. So I'm going to pick a few points. I'm going to pick -1, 0, and 1. So what would you, let's just look at what the actual y coordinates of this function are at this point. So we'd say at -1 it's at, I think, 6, right? At 0 it's at 3. And at 1 it's at 1. So is everybody good with what we did there? We just took the coordinates of these points. Oh, I'm sorry, I meant to say +6. Sorry, was that I think that's the only one I messed up. Yeah, sorry about that.
It's supposed to be 5, but
1, 2, 3, 4, 5. Oh, you're right. So now we're going to look at what the derivative at these points are. 0, -3, and 0, you said, right?
Yep.
So we're going to look at the function and see if this makes sense at those points. Basically, we're going to look at the slope at those points. What would you say the slope is at -1?
0.
Good. What would you say the slope is at 0? Yeah, you'd say probably -4, -3. Wouldn't that make sense for what the derivative graph gives me at that point? It's about what that slope looks like. And then we'd say the slope here is
0.
which makes sense because the derivative function at that point was 0. So do you see how they relate to each other?
Mm-hmm.
Okay, perfect.
That's pretty crazy.
Sure. So by plotting the slopes at the points of the graph y equals f of x, we obtain the graph of the derivative. The slope at point A of the graph of f of x to the left is the y-coordinate of the point on A prime of the graph to the right. So essentially, if we look at any point on this graph on the left here, its slope corresponds to the y-coordinate of this graph. So you see how here at A, the slope is +4,
Mm-hmm.
which means the point is at +4. At C, it's at 0. The slope is 0. It hits at 0 here. At D, the slope is -1. It hits at -1. So do you guys get the gist of this? Okay. So now we're going to try to take the original function and match it to its derivative function. So there's several ways you can go about doing this. So this one here is linear. So we know that linear functions have a, what type of rate of change? Constant, which means isn't the slope of this whole thing always 1? The entire thing is 1,
Mm-hmm.
right? So at any given point, at -2, it's at 1, or the slope is at 1, right?
Mm-hmm.
At every single point, it's at 1. So what kind of function is this going to create for its derivative? A constant function, good. So which answer do you think it is? B.
Mm-hmm.
Why wouldn't it be f, even though that one also looks like a constant function?
There's a hole.
There's a hole in it. So we're going to talk about how that hole kind of comes about. So if we look at the one below the linear function, this looks like two linear functions with different y-intercepts, but they both have a slope of about 1, right? Do you see how the slope on both of these is 1? But there's one issue. Could we assess the slope at x equals 0? No. Slope cannot be determined. We call this differentiability, which we're going to have a whole entire lesson on after into quarter 2. But essentially all you need to know right now is that if it's not connected and it's not smooth, you cannot find the approximate derivative. So what answer do you think this one's going to be? Good. Okay, so we've used F and we've used B. So this one here looks approximately like what type of function family?
Quadratic.
Good, quadratic. So if we look at the slope of the quadratic, it's got, say, like a positive 1 slope, then it flattens out to 0, then it goes down at like a negative 1, negative 2, right? So that means that my function, if I were to graph its function, it's going to be up at 1, it's going to go down to 0, and then it's going to go down to negative 1. So which answer do you think this one's going to be? D. Good. So absolute value function, this piece is a negative slope, this piece is a positive slope. So it's going to always be at negative 1, and then after 0 it's going to jump up to 1. So which one do you think that one is? A. And then why can't we differentiate at 0? Could you determine the approximate slope at that point? No, because they don't match on each side. Okay, so we can't, that's why they use the open circle on that. And then we have this one left. So this one is cubic, right? So it goes up, then it flattens out, and then it goes back up again. So what type of function is up, flat, and then up again? C, quadratic. And then the last one is definitely E, by the process of elimination, but of course this piece is linear, so it's going to be constant. This piece right here, notice that here we can't find the derivative, so it has to be E. So does that make sense so far? All right, so you're going to do 2 sketches for homework, classwork.